Okay, I'm back. And so in our previous segment, we were talking about the three different ways that a nucleus can get rid of energy. So it could get rid of energy by undergoing alpha decay, beta decay, and gamma decay. So I just want to show you that you can start with one radioactive substance and you can end up with a whole bunch of other radioactive substances. So in this picture here, we're going to start with radioactive uranium. So let me put it over here, and we're going to start with uranium, which has an atomic number of 92, and then it has an atomic mass of 238. So this is a particular isotope of uranium that is naturally radioactive. Okay, so the first thing it's going to do is it's going to give off an alpha particle. And so the alpha particle would have been 2 protons and 2 neutrons. So that means that the 92 is going to change into a 90, and then the 238 is going to change into a 234. And so if you look up on your periodic table the 90, because that tells you the identity of the element, then that turns out to be thorium. Okay, now this one is also going to be radioactive. So it doesn't stop just with thorium. So then what's going to happen is that thorium is going to give off a beta particle, and it's going to turn back into, or it's going to turn into Pennsylvanium, so Pa, and it's still going to be 234. So this number here did not change, but this number down here, instead of being a 90, is now going to be a 91. And then this one, now we're not going to do too many more of these, so don't worry about it. But this one is going to give off another beta particle. And so it's still going to be 234. So this number over here is still going to be 234, but it's not going to be 91 anymore. It's going to be 90. But 90 is uranium. So it changes back into uranium. The only difference is now this uranium is lighter than the original radioactive uranium. Well, even this one is still going to be radioactive. So if you want to look at the chart, you can follow it, and you can see that this uranium is going to continue to decay into other things, and then it finally ends up with lead as being pretty stable. So most things, most your radioactive substances, when they turn into lead, they're pretty much done, and they are going to be stable. Actually, iron is the most stable element in the periodic table, as from a point of view of its nucleus. We're not going to get into it, so don't even worry about it. Let that drain out of your head. There it goes. Okay, so let's get back to this. So what I wanted you to see was that you can start with one radioactive substance, and then it decays into a lot of different kinds of substances. And so this is going to be called a decay series. Okay, now each of these decays at a certain rate, and we're going to call this the half-life. So the half-life is going to be the amount of time it's going to take for a particular radioactive substance to decay until half of it is left. So let's first look at the graph. So we've got this graph, and the up and down part is going to be the amount of radioactive substance. The sideways part is going to be the amount of time that elapses. So up at the top, you notice you start with 100% of a radioactive substance. So let's say that we start with 100% of this thing up here. Okay, now after one half-life has gone by, and so I don't know offhand what the half-life for uranium is, so let's just say for the sake of argument it's 1 billion years. Now I'm definitely wrong on that, but let's just say that it's 1 billion years. So after 1 billion years has gone by, one half-life, now the sample would contain 50% of this stuff and then 50% of whatever it turned into. Now after two half-lives goes by, now let's be careful, you might be thinking, well, if half of it goes after the first half-life, then half of it should go after the second half-life, and you shouldn't have anything. Well, it's half of a half. So it went down to half of the original material, and then after another half-life, it would be half of that, so then it's down to 1/4 of what you started with. And then after another half-life goes by, then you'd be down to 1/8 of what you started with. So this decay series, this curve here, is called an exponential. And so there is a formula that will allow us to calculate how much time, t, so t for time, how much time would it take for a particular material to decay. So in that formula there, which you're not going to use, but in that formula, n sub 0 means how much did you start with. So that's the original amount of radioactive substance. N is going to be the amount that you end with after a certain amount of time, t, has gone by. And then the t half-life means that's the half-life, and for every radioactive substance, it has a different half-life that goes with it. So the half-life for uranium is going to be different than the half-life for thorium, and this is going to be different than the half-life of Pennsylvanium. Okay? So there's a little formula there that would allow you to exactly calculate how much material will be left after a certain amount of time has elapsed. But we're not going to use that. We're going to use something a little bit simpler than that. Here is different half-lives. And again, I know that that's really small and it's hard to see all of those numbers, but it shows the half-lives for all of the different elements that were in this picture here. So you can find the half-life for each of those different nuclear reactions on this somewhere. Now all I want you to see is that some of the half-lives are in minutes. Some of the half-lives are in seconds, which means it doesn't take very long at all for that particular radioactive substance to decay basically to nothing. But then you got other ones on that list that have half-lives that are in the billions of years. So it takes a long time for those radioactive substances to decay. So this is one of the problems with nuclear energy. So nuclear fission is that it produces radioactive waste. And some of that waste decays very rapidly, and you don't need to worry about it. But then there's a few of those radioactive waste products that have very long half-lives, and that means we need to store them and leave them alone for thousands, maybe millions of years for them to completely decay away. All right, so here is the kind of question that I would like for you to be able to do on an exam. So suppose a rock has a radioactive isotope that has a half-life of 500 million years. And now when we look at this particular sample, we notice that only 1/16 of the original amount is there. How old must the rock be? So we're going to assume it starts out with 100%. And then after 500 million years goes by, half of it is going to be left. So all you got to do is make up a chart, and in one column is going to be the amount of time that has elapsed. And then in the other column over here, you're going to write down how much is left over. So we're going to start our stopwatch at 0. So after 0 years have elapsed, how much of the material do you have? 100%. So we're going to start with 1. Okay, then after one half-life has gone by, and one half-life is 500 million years, it's now down to 1/2. After 2 half-lives, so now we need to take 500 plus 500, so that's going to be 1,000 million years or 1 billion years. Now it's going to be down to 1/4. And then we can go down to 1/8, and then we can go finally down to 1/16. So the number there is that's going to be 2,000 million years or 2 billion years. So 2 billion years have elapsed, and now it's down to 1/16 of what it used to be. So that's the kind of question that you should be able to do on the exam. Now you can do the question with that formula as well, but you don't have to. So a chart is just as good as using the equation in this particular case. In other cases, the formula would actually be the better way of solving the question. Okay, so let's take a break, and when we come back, we're going to talk about what kinds of radioactive isotopes are normally used in dating rocks.